Hi, I'm Wan-Hsuan from UCLA. Today I will present our work, Scalable Optimal Layout Synthesis for NISQ Quantum Processor. This is the overview of my talk. First, I will introduce the quantum layout synthesis problem. Then, in the second part of my talk, I will present our work OX2. So let's begin with the introduction to quantum layout synthesis problem. The input to quantum layout synthesis problem is a quantum circuit and a coupling graph. Each vertex in the coupling graph is a physical qubit. Only two adjacent physical qubits can perform a two-qubit gate. For circuit, each line represents a program qubit. The box on lines are quantum gates. In layout synthesis, our goal is to map each program qubit in the circuit to a physical qubit and schedule gate execution time. This shows a valid layout synthesis result. First, we have mapping from program qubit to physical qubit and time coordinates to indicate the time to execute a gate. We need to execute all gates in the input circuit with correct order. Then, to have valid two-qubit gate execution, we may use some extra swap gate in the circuit to change the mapping. The objective in layout synthesis problem can be either minimizing the circuit depth or swap count. I will use an example to show why we need swap gate. Given a circuit and a coupling graph, assume initially we have the following mapping. Then, based on this mapping, we will execute gate 0 on this physical qubit, and similar for gate 1 and gate 2. Previously, we have mentioned that the two-qubit gates can only acting on two adjacent qubits. For gate 3, we can execute it because it is acting on adjacent qubits. We can also execute other gates until gate 10. Under this mapping, gate 10 needs to act on a pair of non-adjacent qubits, so we cannot perform this gate. Thus, we need to insert a swap gate to change the mapping. After insert the swap gate, gate 10 is acting on two adjacent qubits. Next, I'm going to introduce a previous work OSC. It is an optimal layout synthesizer. It encodes layout synthesis problem as an SMT problem and uses the optimization module theory solver to obtain optimal results for either depth or swap. However, their scalability is limited. Therefore, in this work, we improve upon OSC by proposing a succinct formulation, better SMT encodings, and use an efficient optimization method. After applying these techniques, we can achieve hundreds of times of speedup. Next, I'm going to introduce our first improvement, succinct formulation. In OSC, we have four types of variables. First, we have a mapping variables for each program qubit at every time step. To represent a physical qubit in map 2, for example, for program qubit 0, it's mapped to P3 initially. Then, after time 7, a swap gate is inserted, so its mapping variable is changed after time 7. In addition to mapping variables, we have swap variables, which is a Boolean variable to indicate whether there is a swap gate inserted on an edge at a certain time step. Then they have time variable for each gate to represent the gate execution time. Lastly, they have space variable for every single n2-qubit gate. However, this is redundant because the gate position can be inferred by combining the mapping variable and time variables. Therefore, in our formulation, we remove this type of variable. Thus, we can get rid of some constraints related to space variables. For example, consistency between mapping and space variable is no longer needed. In addition, we need to modify constraints using space variable by rewriting them using mapping and time variable. In addition to the above modification, we have a few types of constraint, which is valid two-qubit gate mapping constraint to ensure that when the two-qubit gate is scheduled to be executed, its target program qubits are mapped to adjacent physical qubits. For example, for gate 3, since it's scheduled at time equal to 1, at that time its target program qubit must be mapped on a pair of adjacent physical qubits. Let me use an example to demonstrate the effectiveness of our new formulation. These two tables show the number of variables and constraints of the formulation that encodes the problem to map a 20-qubit QAOA circuit to a 5x5 grid coupling graph. For variables, we use 30 less variables. For constraint, we can reduce by 24% compared to NISQ, which can bring us around 14 times of speed up in SMT solving time. Next, we are going to talk about our optimization strategy. In NISQ, they use the optimization module theory solver in Z3. However, we find it slow compared to only check satisfiability, and it may not return a valid solution with limited time budget. Therefore, our goal is to obtain a valid solution efficiently and iteratively refine the solution within the limited time budget. Our strategy is to add a constraint to bound the value of the objective. We will iteratively modify the bound and only check satisfiability through Z3. During each iteration, since only one constraint is modified, we apply incremental solving technique to prevent duplicate work. For depth optimization, we will add this constraint to restrict the gate execution time. We will start with a tight bound to initialize the solving process by easier problem, and iteratively increase the bound until we obtain a satisfiable assignment. For swap optimization, we have the cardinality constraint to restrict the number of swap variables to be true. We will perform a two-dimensional search in depth and swap count to generate the Pareto optimal solutions. This figure shows an example of our search process. We will start with a depth optimal solution, iteratively decrease the bound until the model is unset. The last satisfiable assignment is the Pareto optimal result. Then we increase the depth bound and try to decrease the swap count again. The process ends when increasing depth cannot reducing the swap count, or we run out of the time budget. Next, we are going to introduce the use of coerced grand circuit model. Our transition-based model is inspired by TB-NISQ. They reduce mapping variable by using the concept of gate blocks and transitions. Within a gate block, the qubit mapping remains the same. Between gate block, mapping transition happens to change the mapping by swap gates. Here is the complexity analysis of using TB-NISQ. According to the table, we can see that by using the transition-based model, we can largely decrease the number of constraints. If we use the previous QAOA circuit and coupling graph as an example, using TB-NISQ can reduce the number of variables by 49% and the constraint by 81%. This leads to 1,600 times of speed up compared to NISQ. Our last technique is exploration of different encoding schemes. In Z3, variables can be encoded by different types. Take mapping variables for example. One naive encoding is using integer to represent. Since in our formulation, the variable range is finite, we can also use a fixed-size bit vector to encode. For example, assume the range of mapping variable is less than 8. We can use a 3-bit bit vector to encode it. For example, when the mapping variable is 2, we can use bit string 010 to represent. The advantage of using bit vector is that we can reduce the problem into set problem and thus can be solved by a set solver. We can even use an uninterpreted function to encode all mapping variables. The advantage of using EUF is we can have a compact encoding for injectivity constraint. Without EUF, we have quadratic number of injectivity constraint, but with EUF, we can define an inverse function and use linear number of constraints to enforce injectivity. Using different variable types will trigger different theory solver and have different constraint encoding strategy. Both will affect the solving time. This figure shows the speedup comparison of using different encoding strategy. Using NISQ formulation and integer variable encoding is our baseline. We compare the speedup of using different encoding scheme. We can see that using big vector gives us the best performance. We posit that the reason might be the set solver is the most powerful solver among all other theory solvers. In addition to variables, we can use different strategy to encode the cardinality constraint. If we directly use at most function is in 3, it will invoke pseudo-Boolean solver. But if we use CNF to encode, we can invoke a set solver. This table shows the runtime of using two encoding schemes. Here, using CNF outperforms using at most function in all cases. Lastly, we present our optimization results compared with other layout synthesizer. Compared to Sabre, we can reduce the depth by 70% and swap by 93%. Compared to SetMap, we can reduce the swap count by 62%. In the end of my presentation, I would like to discuss some future direction to further improve the scalability. First, we plan to develop parallel version of NISQ. Since swap optimization usually takes many iterations, it offers a good opportunity for parallelization. In addition, we observe that using different encoding strategy to convert cardinality constraint to CNF has large impact on solving time, but we didn't find the best in the class strategy, so it is worth to have a portfolio approach using different strategies. The second direction is to explore the power of max set solver to perform optimization. And then we may guide the set solving process using application-specific heuristic algorithm. For example, we may be able to provide a better variable ordering for set solver. So this is the end of my presentation. Thank you for your attention.